Shane.
Hey, are
How
you?
are we done with the chem viz? Like we're almost there, right?
Um, think so. Yeah,
40.
we're almost done.
Okay. Is this the passage we were working on or
Mm-hmm.
yeah. Normal glycogen. What type of bond is decreased in Lafora bodies? I don't think we read the second half of this. Lafora disease is a fatal progressive epilepsy that is characterized by the formation of deposits of sparsely branched insoluble glycogen-like polymers called LBs. LBs contain a larger amount of covalently linked phosphate compared to normal glycogen. The abundance of phosphate has been linked to a mutation in the gene for laforin, a phosphatase specific to carbohydrates. Is that enough, or should I keep reading for this question?
Uh, okay. Yeah, you can answer it from what you just read.
What type of bond is decreased? Aren't they normally linked by alpha 1 to 6 linkages?
Tell me what you mean by that.
Like 1 to 6 is here and 1 to 4 is here. Or
The
4, 6.
the one is here,
So
two,
6.
three, the four is there, and the six is here.
Oh, okay. So 4 is when it connects from the hydroxyl group and wait, from the carbon.
Huh? So,
They're normally 1 to 4 linkages because they link
mm-hmm.
here.
Uh-huh.
If
And
that's the normal linkage, and these,
so what was the other type of linkage?
there's alpha 1 to 4, 1 to 6, and then there's the beta linkages.
So tell me about the 1 to 6.
That's from the carbon right here. So those are like,
Well, it'll be attached to
uh, but it like links differently because these are
like that.
like you right.
So the linear chain, remember I drew something like this.
Yeah.
So the linear chain is going to be 1, 4,
Yeah.
but you also will have branches that will be like this. This is
Those
the
are the 1 to 6 linkages.
correct.
And if they're saying that they're sparsely branched, then that means that there's fewer of the 1 to 6 branches.
Mm-hmm.
All of four bodies.
Yep.
The 1 to 4 like bonds stay the same and that forms the general structure.
Yeah, this would be
The
1,
same.
4.
Mhm.
Then these branches
Or-
6.
And phosphomonoester.
Mm-hmm. So phosphodiester and monoester are phosphates
Um,
bonded uh to themselves like this. So this is the like this is the entire like phosphate diester. Monoester would just be like this one. So those are the ones that'll be present, like the phosphodiester, phosphomonoester. Those will be the ones that are present in ATP, ADP, AMP, whereas the glycosidic bonds are going to be the bonds within the glycogen between the glucoses.
mhm. Okay.
So what should this be?
There's only one bond to itself.
Oh no, I mean so for this question.
Oh, well, for this question, it's 1 to 6.
Yep.
Then you meant with the like phosphester and monoester. Okay.
Mm-hmm.
Okay. Like, so there's object length and image length, right?
Mm-hmm.
And where there was a question about that, and it was like I like over O.
Mm-hmm. So the formula for this, um, if you don't remember it, it's 1 over focal length. This is a thin lens equation. 1 over object distance, 1 over image distance.
Yes. So 1 over 3F plus 1 over F, right?
Uh,
This is 1F and this is 3F, this distance.
the object distance, uh-huh.
So would that be 1 over 4F?
You could try doing the math.
Do I plug in a value? Like, do I plug in 1 here and 3 here?
Well, they're giving you the object distance in terms of focal length.
And F is for focal length.
Mhm.
This.
So you could plug in,
F
yeah,
equals 3F plus I.
plus a 1 over I.
Whenever I, yes. So then you subtract on both sides. Hold on, I need to draw this out. Minus 1 over 3F. So it's 2 over I, which means that reverse would be D.
So what are they asking for?
Height of the image, ratio of height of image to height of the object.
Uh-huh.
So this is the image height is 3 over 2.
Uh-huh. Mm-hmm.
Height of the object. We only know it is 1 over 3F.
Yeah, and this is also the image distance is this, right?
Yeah.
Mm-hmm.
Over, okay, so now it's 1 over 3F.
Mm-hmm.
No, because that's multiplication needs to be division, so it's 3F over times 3F.
So you're dividing it by multiplying it by its reciprocal, right?
Right, but then that means that it's 3F over 1.
Mm-hmm.
I wanted to try to
Oh,
figure this
sorry.
out.
So we need the image was 2 over 3F and objects. If the
Oh, so I already have the reciprocal.
Yeah.
No, because that's 1 over image. Image is 3 over 2.
Oh my bad. But yep, and then object is 1 over the
3F.
F
So
and
and 3 cancels out, you're left with 1/2, but wouldn't it be F squared?
Well, if you're dividing these, so that would be 3/2f times.
Times 3/1.
Uh, hmm.
That's what I'm saying. That's like more complicated.
Uh, let's see. 3f/2 O is oh. So okay. Object is at 3f, right? So 1/3f is 1/object, but object would be at 3f, right?
Yeah.
So yep, you're dividing it by 3f, which is the same thing.
1/3. Okay.
Yeah.
Okay.
This should be
So then the 3's cancel out, you're left with 1/2.
yep.
And the F's cancel out as well.
Mm-hmm. Good. So yeah, remember this equation, and this is also pretty much magnification. Magnification is -I/O.
Okay.
Mm-hmm.
That's like the opposite of the equation, right? Because it's 1/F. So is, oh, okay, no, I see it.
Mm-hmm. So that's kind of like what we're doing here, just without the negative sign.
Okay, cool.
So key here was to know that equation, and then also to make sure that we are answering the question.
Mm-hmm. So you think I like just found the image and plugged that in? No, because
But
at first I just got 2/3.
as 1/image, right? And the image would have been the 3/2f.
Yeah. Mm-hmm.
But yeah, always make sure we give them what they ask for.
Okay, cool.
Yeah, one of my students that just took the test told me that there are a lot of calculations on it. So get ready.
But do you think that it's the same one for like the same month?
Oh no, it'll be different, of course, but I would still it'll be different, but it won't be like completely different. Like if they decided to show more calculation problems on this recent one, they'll likely do that um on the next one. But anyway, overall
Okay.
reaction for the decomposition of hydrogen peroxide shown in reactions 3 and 4. Okay. So this is when you like can cancel out terms that appear on both sides. I mean, both sides of reaction 3 and reaction 4.
Mm-hmm. But that's what I was looking at because
Mm-hmm.
here it got reduced, right?
Mm-hmm. Yep.
What's the difference between aqueous and liquid?
Aqueous uh is not, so liquid would be a pure substance.
And aqueous is like submerged in a substance?
Yeah, like in water. So like H2O2 aqueous would be H2O2 in like mixed in water. And the I minus is the iodide mixed in water. So we use like whenever we do like our K expression stuff, we include aqueous stuff and gas stuff because those can exist as mixtures, um, which means that they can have like a certain concentration, right? Whereas like H2O liquid is 100% H2O, nothing else is in there. So we don't use, at least when we do, like, we're not doing a like equilibrium, like K EQ thing here, but if we did a K EQ thing or a Q, then we would not include the pure substances because they're 100% like what they are.
Okay.
But for this, basically, like, if we have like, uh, you know, like two steps, two step or whatever type of chemical reaction, we essentially like can cancel things out, like, because it's basically like this and then that to turn into this, like, this is the stuff that starts it off, this is the stuff that ends it, and the stuff in between we can kind of cancel out. So another way of saying this, like they're saying the overall reaction is like the overall net reaction.
Mm-hmm.
So for instance, this and that can cancel.
Okay. So
This,
that's ended up without the IO.
what's up?
Nothing. Never mind. I was just saying that like so that cancels out A and B.
Mm-hmm. All right.
But then is it two H2O2 because there's one and two?
Mm-hmm.
And we're talking about the net reaction.
Yep.
And then here we have H2O and H2O, so that's two of them, and then we only have one oxygen left. So that's D.
Mm-hmm.
Okay. Wait, can you explain one more time why we crossed out?
Mm-hmm. Yeah, so the net reaction, like it's basically like H2O2 plus I minus yields IO plus H2O. And then the next one is H2O2 plus IO minus yields H2O plus O2 plus I minus. So if we have like these as the reactants producing these products first, and then these reactants forming these products, like for the second step of this, um, we don't need to like rewrite the intermediate steps because they ultimately
That reaction.
be,
Okay, but how is this an intermediate step if it's in the first portion?
oh no, I just mean like these as the intermediate steps. It's
Mhm.
just that if you have something that's in your reactants and like products as well, then that's not going to like factor into that overall net equation.
Right, but this, oh, because you're saying that this and this don't change?
Uh just because, so for instance, so this turns into this iodide ion here, and then we have the iodine there, so it's balanced on both sides. And then here we have this part and balanced with this part. So we have, an equal amount of iodine on both sides, and it's just one, like, mole of it, right? But if you were to add them all up, you would end up getting like IO minus plus IO minus, which would give you 2 IO minus, and then 2I minus here, 2I minus there. But that's not actually what happens. It's not actually going to double the amount of IO. It's just that this I that turns into this IO, that IO breaks down into the O2 and the I. So it's just like if you wrote out the entire and if you wrote out the entire reactions, you would see that if we get something for step 1 that's a product, and in step 2 is a reactant, then in the overall reaction, the stuff in the middle would have to cancel because we're really going from here to there.
Okay. All right. I understand.
Oh,
Hold on. This one. We go over this.
mhm.
I'm not sure what an automobile catalytic converter is.
Um, let's see what they're saying here. Okay, a catalyst is a substance that speeds up a reaction without being consumed. For example, V2O5 is used as a catalyst to oxidize SO2 to SO3 in the first step in the production of sulfuric acid, reactions 1 and 2. Furthermore, H2O2 can be decomposed with the aid of a catalyst, as shown in reactions 3 and 4. Catalysts are widely used in automobile catalytic converters, where the exhaust gases are passed through beads of a solid catalyst. The catalyst aids in the conversions of carbon monoxide to carbon dioxide. Okay. Hydrocarbons to carbon dioxide and water, nitric oxide to nitrogen gas. Unfortunately, the catalytic converters can also can catalyze the oxidation of SO2 to SO3, which subsequently reacts with moisture to form unwanted sulfuric acid. Okay, let's see what they can scroll down a little bit. All right, catalysts are classified as either homogeneous or heterogeneous. A homogeneous catalyst exists in the same phase as the reactant molecules, whereas a heterogeneous catalyst exists in a different phase than the reactants. Okay, so
Okay, so I
apparently,
guess that makes sense. If it can go to S from SO2 to SO3, it can't go backwards, right?
um, let's see.
Which reacts with moisture to form sulfuric acid.
Okay, yeah,
SO3 and H2O
yeah,
forms
that's
sulfuric.
going backwards.
Huh? Yeah. Because the rest CO to CO2.
Mhm. Yeah, we have hydrocarbons like methane to CO2 and water, check. Nitric
Where's that?
oxide to nitrogen gas, check. Carbon monoxide to CO2, check. And then, yeah.
It's the opposite. Okay. Guess that was an easy one. This one I got right. So
Oh, so this is, uh, like, okay, well, so sorry, what were you thinking?
I remember I was really confused about this problem and how to answer it because in my head, I thought that like finely ground, that means that it doesn't like catalyze the reaction the same way,
So
right? Because
you
it,
compare like a sugar cube to like whoops, like sugar, like powder, like, and you wanted to get your coffee like to be sweet as fast as possible, what would you use? This or this?
The finely,
Yep.
like, because it would dissolve faster.
Because it has a higher surface area, right? So these individual, like this is an enlarged drawing over here of a sugar like powdered grain or whatever. Uh, the water can solubilize it like all over. Whereas like the cube of sugar, the water can only touch the walls or the faces of the sugar cube. It can't touch the stuff on the inside. So what you're doing by finely, grinding it is increasing the surface area, which makes it, as you said, soluble, like a lot more soluble. It's the same thing with the previous passage about glycogen. Um, Glycogen has the branches to increase surface area so it can be more soluble. That's why when it said that the Lafora bodies were sparsely branched, insoluble, it's because they have less branches, therefore less surface area. So that's something that is one of these are kinetic properties as opposed to thermodynamic properties. Thermodynamic properties deal with stability in terms of like energy, of like, a reactant and a product and the reaction. But activation energy, which is like the hump thing, could be lowered by a catalyst and therefore change the kinetics or the rate of the reaction to be faster. And two other things can do that. One is temperature, that can also make things go faster. And then the other thing is the surface area of the catalyst. So if you grind it up, you'll get more surface area, which means that it can, as you said, dissolve better and faster.
Okay.
Yeah, greater surface area of the catalyst will be exposed.
That means it'll be okay. Cool. Let's do this one.
Okay.
Aluminum is placed. How does Hg evolve? Aluminum, it does not studied. Do we need to read this?
Yeah, you could read it.
Okay. A group of students investigated the reactions of several metals with solutions containing metallic ions. Students placed a strip of metal into solutions containing different metallic ions as shown below, shown in figure 1. After several hours, they observed whether Y formed on the surface of the metal strip as see table 1. Students placed a solid strip onto each metal into the aqueous solution containing ions of the same metal. Complete circuits were established. Finally, the students checked a general chemistry text to determine the standard deduction potentials of the following reactions.
So,
Space off.
yeah, what's up? So,
Of Z and this. If a strip of aluminum is added, it's a new solid.
so okay, let's scroll down for a sec. I want to ask you something. Okay, so compared to reaction, like the reaction 1 to reaction 2, which is the one that, so we're given half reactions, right? Which are just like in redox, there's like a reduction half reaction. There's an oxidation. There must be there must be an oxidation half reaction as well. Now, compared these two, which would be reduced? Because they both can't be reduced, because in redox you need something to be reduced and something to be oxidized. So how can we tell which one gets reduced,
Two.
which one gets oxidized?
Um, periodic trends, it's PB and CU.
So the thing with the higher, so uh so it's not going to be like a periodic trend thing, but the half reaction with the higher reduction potential will be the one that gets reduced.
Isn't that? How do you predict reduction potential? Isn't that like electronegativity?
So it's not going to be something that we can readily predict, but for the two examples I'm talking about that are giving us the values.
This. Hold on.
Yeah. So these are reduction half reactions, which show essentially like, a cation form of whatever, a metal plus electrons, because gain of electrons is reduction. And so you'll see by default, a lot of times it'll just be drawn or written out as a reduction half reaction. But it doesn't mean that it's actually going to be reduced. So whichever thing has the higher reduction potential, right, will be the one that gets reduced.
But the higher reduction potential would be the negative charge.
Oh, just whichever.
Oh, this is 3.99.
Mhm. So in this case, this
C.
gets reduced. Now that must mean
The other one gets oxidized.
yes, which means that this reaction would go that way.
Yes.
And the reduction potential, so the reduction potential is negative of the oxidation potential. So this oxidation potential will be positive 0.127 volts. Okay.
Yeah.
All right. So that's just the general rule for electrochemical cells. If it's an electrolytic cell, it's the other way around. But yes, whichever thing has the higher reduction potential will be reduced, which means it'll gain electrons. And whichever half reaction has a smaller reduction potential will get oxidized, which means it will lose electrons. So if I were to write this out, it would be like PB solid yields PB2 plus 2 electrons. And I can connect it. Oh, and this could be an example of like that net reaction thing. So I can connect this to Cu2 plus 2 electrons yields Cu solid. And you see how the 2 electrons are produced here, but are used up here. So we can cross those out like we did with that question with that
Remember.
reaction, right? So
Yeah.
this would be the overall reaction. Okay. Now we can additionally see that if we have reduction, we are having some metal cation turn into some solid, right? Whereas if we have oxidation, the solid dissolves into the aqueous solution.
Okay.
right? So now that we know this, we can use the information up top in that table to figure out, here you can go up on the left. Yeah. So we can use this information to figure out things about, whether something gets reduced or oxidized or, nothing. So for instance, when they use a strip of zinc, which means a metal solid zinc like this,
HCl evolves.
yeah, with HCl, then that means that the H2 gas, like I guess the HCl turns into the H2 gas. And they're telling us here that since this is happening, the reduction potential of zinc, um, well, okay, yeah. So so HCl would be like a +1, -1 for the Cl, and H2 gas has a 0 oxidation state. So this would be gaining an electron, right? Which would be reduced. But let's see. For the zinc, okay. Okay. So zinc then should be oxidized, right?
Yes.
Mm-hmm.
Wait,
Now,
would it be getting reduced?
so
Because
if they're placing a strip of
wait,
zinc,
which one? Hydrogen or HCl?
oh,
It's getting rid.
oh yeah, the hydrogen in HCl, I should say. Like,
Oh, no, it is getting oxidized. You're right. Because
yeah, I could even write it as because it dissociates into H plus.
what would it look like if it got reduced?
Um, oh, that this is if it's reduced, if it gains electron.
Oxidized.
But zinc, for instance, which is a solid, would have to get oxidized here, which would make it zinc.
A positive charge.
Yeah, yeah. So I guess zinc 2 plus 2 electrons.
Mm-hmm.
So that 2 electrons means that this we multiply by 2, and that makes sense because we get H2 gas at the end. But okay, so this is telling us that the hydrogen is getting reduced, right? The H plus.
Okay.
And if that's true, it means that the reduction potential of hydrogen is larger than the reduction potential of zinc, right? Because whichever thing has the higher reduction potential will get reduced.
Right. So that means that going in the opposite direction with aluminum,
So now
if
for
HCl got oxidized
so
into H2.
so so we know that hydrogen's reduction potential is larger than zinc's reduction potential. But now we can compare zinc with aluminum and see which one gets
Reduce.
reduced. Oh, wait, sorry, a strip of aluminum. Okay, so that means that we're comparing. So what we can do is we can compare zinc and aluminum. For instance, if we have the zinc strip, and aluminum cation, there's no change in the composition of the metal strip. If there's no change, it means that the zinc stays
Same.
the solid and the aluminum doesn't change either. Now, if we have
It's for
Mhm.
this row.
Yep. So that's if you have the strip of aluminum and the zinc cation, and it says new solid. What do you think that new solid would be?
It forms a different thing, so that means that something got oxidized and something got reduced.
Uh-huh. So, but what can the new solid be?
Aluminum.
So that would be the old solid because we're using the aluminum strip and we're adding the zinc. Bless
I
you.
don't know. There was like a zinc solid at some point, right?
Yep, that must be what that new solid is, right? Right? Because if it was no change, it would like so for this, no change means that we have zinc solid that's not changing and aluminum 3 plus, which is also not changing.
Mhm.
But if we have aluminum solid and zinc cation, we have a new solid. And if it was aluminum, it'll be the same solid, so no change. But we see it's a new solid, which must mean that the zinc 2 plus is getting reduced to form the new zinc solid.
Okay.
So this is saying that the zinc is getting reduced, which means that the aluminum is getting oxidized, right?
Yes.
And so if aluminum is getting oxidized when zinc is getting reduced, and the thing with the higher reduction potential is what gets reduced, the reduction potential of aluminum, whoops, should be smaller than that of zinc.
Which means one that gets oxidized.
What's up?
You said the one with the smaller reduction potential gets oxidized.
Yes.
Okay.
Since we know that hydrogen has a higher reduction potential than zinc, and now from this table, we know that aluminum has a lower reduction potential than zinc. When they ask us if H2 gas evolves when you have aluminum, well, it evolves when you have zinc because it's larger than zinc in terms of reduction potential. And if zinc's reduction potential is larger than aluminum, then hydrogen's reduction potential must be larger than aluminum.
Hmm.
So takeaways here, whichever. So in redox, you'll have half reactions. One half reaction is reduction, one is oxidation, and whichever half reaction has a higher reduction potential, that one will be the one that gets reduced.
Hold on. I can't hear you. My
Mhm.
Siri turned on.
Oh yeah, you're probably gonna get to plug your computer.
Sorry, a second. But sorry, repeat that. I
Yep.
didn't.
So 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 in redox, there's both reduction and oxidation within the same reaction, but you can break the reaction into half reactions where you have a reduction half reaction and an oxidation half reaction. Now, a lot of times they won't tell you that something will get reduced and something will get oxidized. They'll just give you reduction potential values, and whichever reduction potential is larger will be the thing that gets reduced, and whichever reduction potential is smaller will be the thing that gets oxidized. And oxidation is just the reverse of getting reduced, which means that the reduction potential, if you want to turn it into an oxidation potential, you just multiply it by -1.
Okay.
So for this, the key thing here is that we're using qualitative information in table 1 to see that, okay, if they're telling me in the question stem that zinc reduces hydrogen, that means hydrogen has a higher reduction potential than zinc. And then they're asking if aluminum does that as well. So then we can compare aluminum to zinc, and we see that aluminum in the presence of zinc, aluminum gets, sorry, the zinc gets reduced, which means the aluminum gets oxidized, which means the aluminum has a lower reduction potential than zinc. And since we know that hydrogen has a higher reduction potential than zinc, hydrogen must have a higher reduction potential than aluminum as well. So H2 gas, if that evolves from zinc, it will also evolve for aluminum.
Okay. Cool.
So yeah, thing with the higher reduction potential gets reduced.
Shoot. Okay. I didn't select an answer, so
Mm-hmm.
should I scroll down?
Mm,
I,
yeah. Well, let me see.
I can't
That
like
a circuit similar to that in figure 2 is set up in which X equals aluminum.
xn plus equals aluminum 3 plus.
Mhm.
I don't see xn. Oh, here, right here. Y equals Cu and Cu2 plus.
Mhm. Got it.
Okay. But I kind of need to see the.
Mm-hmm.
Okay. When in the metal strip, um, do we have to use the table or no?
Um, yeah.
Or is it new solid, so the aluminum is getting reduced?
The the what? Maybe.
Didn't we say that zinc got oxidized to form the new solid? Oh, aluminum formed the new solid.
Oh, if it
What?
forms new solid, it's going to get reduced, right? Because the cation gains the
Um, the aluminum is the one that's getting reduced because
for
I'm saying the X is based off of this. The X is the solution, and then aluminum is the new solid.
so this is just saying that we have an aluminum strip with some aluminum cation, and we have a copper strip with some copper cation.
There
But
won't be a reaction between each of these things, but the voltaic cell, wasn't it like positive charge and negative charge here?
so how do we know that nothing's going to happen?
Because aluminum won't react with aluminum, they're the same.
So okay, we have both copper and aluminum, and we want to see if something happens with when we have both of those, right? So the table 1, we can use that for information here, right? Like for instance, if you had the copper strip with the metal aluminum cation, you're right, you get no change. Nothing's happening there. But now, what if we had our
All right, like these say not studied within one container.
uh-huh. But now let's try the aluminum strip with the copper cation. We get a new solid, right?
Uh-huh.
And what did we say the new solid must be?
Reduced.
Oh, I mean like the identity of the new solid.
Aluminum.
So if it was aluminum, it would be the same thing that we start off with, right?
Oh, so the metal ion or the metal strip? The metal strip has to be aluminum and copper.
So if we're using an aluminum strip with copper cation and they're saying a new solid is forming,
They're introducing a third thing.
uh-huh. Yeah, which will be kind of like just the second thing, which is a copper solid, right? That's how we did. So like the previous question, that's how we did that one. That's when we compared, what was it? It was like zinc to
And
aluminum, I think. But that's what you're seeing here. Like if it says no change, it means
but how do you like, but it would be still copper solid, right?
you'll still have your copper strip there and your aluminum strip on the other side. But we want to see if so in order for this light bulb to turn on, we need electrons to travel through the like wire, this wire, right? And in order for electrons to travel through the wire, something has to be getting oxidized and something has to be getting reduced to have that flow of electrons.
Uh-huh.
So if we take aluminum solid and copper 2 plus, and we get a new solid, that new solid must be solid copper. Because if it was solid aluminum, that wouldn't be like new solid, right?
Yeah.
So Cu2 plus, new solid means it'll gain 2 electrons to become Cu solid. Whereas the aluminum solid would get oxidized. So it will turn into aluminum 3, oops, 3 plus 3 electrons. And then you would just have to balance these two. But basically, what we're trying to do is we're trying to think because again, if you go back to just thinking about how when you have a redox reaction, whichever species has the higher reduction potential will be the one that gets reduced. And so if we're comparing aluminum with copper, right, we can first compare a copper strip with the aluminum ion. And if it was the case that aluminum gets reduced, we should see aluminum turn into aluminum solid, but we don't, right? We see no change.
Mhm.
But when we have the aluminum strip and copper cation, we do see a change. We see a new solid form. And that new solid must be copper solid, which must mean that copper, that ion, metal ion, gains electrons to become neutral copper solid, which means that the reduction potential for copper is
Yes.
larger
Right.
reduction potential
For
of
aluminum.
aluminum.
But if
Mm-hmm.
we still have to balance them in order to
Yeah,
get one of these.
yeah, yeah.
So
So
do it
this,
like a net equation the same way, like what's on which side of
mm-hmm. Yep. So yeah. So we can multiply the aluminum by 2 and the copper thing by 3. And then
Because
you get your 2 aluminum solid plus 3 copper 2 plus aqueous plus 6 electrons yields copper solid plus aluminum 3 plus aqueous plus 6 electrons. And then the 6 electrons, since they're on both sides, we can cancel them out. And you should be left with this. Oh, and then this should be 2 and 3.
can we, I don't understand why you did 2 and 3.
Oh,
Like what,
just to make it, because here you could see that aluminum makes a 3 plus.
3E and the T 2E, so we wanted to get it 6E so you could cancel them out.
Yeah.
Okay, that makes sense.
Hmm.
All right. 2 more. Well, hopefully not. That figure in F2 in figure 2 is set up. So we have the same thing except now PB. PB to CU has no change, which means that there is no, so then no.
So now, fortunately for this, they give us the values. If you look at figure 2.
Right, so do you just, wait, but if no, then if it won't occur, do you just add them?
So do what I said first, like which one gets reduced, and then what do you do from there?
Well, would either get reduced if it's this way, if there's no change? Because we've always been talking about like new solid.
But they're giving us values for this one, so we could just use those values.
Well, this one would get reduced to CU.
Yeah. Now, that means this one gets oxidized, so its oxidation potential will be what?
Positive 1.27.
Uh-huh. Now, cell potential could be, there's different ways of writing it. I mean, there's like cathode minus anode, but there's also, I think it's easier to just do reduction plus oxidation.
Uh-huh.
So what would that be?
300 plus 100, it's going to be positive 400.
All right, now there's this formula.
Fe cell.
Yep.
And
Now, what would this help us indicate?
delta G. I don't remember what it solves for.
So like the delta G, what is that? What's yeah, what does that mean?
S.
So
Gibbs? To
Gibbs
use Gibbs.
now if
So if it's spontaneous or non-spontaneous.
yeah,
So if S is positive, then it's spontaneous
when you said if what is positive?
S. But like I'm thinking in
Yes.
general, when G is S and when H is negative, it's spontaneous, right?
Oh wait, you're talking about entropy?
That's a
Well, this one
yes.
doesn't include
I
that.
know that it doesn't have it. I was just trying to think like as far as like it could help us figure out if it's spontaneous or not.
Yeah.
Trying
So
to make the connection to what delta G does. Okay, but now that it's NFE cell. So
yeah, so what would make something spontaneous and not spontaneous?
spontaneous is negative delta G.
Good.
N is a constant, E cell is positive.
Mm-hmm.
So it's negative delta G,
Mm-hmm.
but it's positive 0.46, so it's this.
Mm-hmm.
Okay.
So now you see that if you have a positive cell potential, you have a negative, because there's a negative here, delta G, which means it's spontaneous.
Cool.
Mhm.
I got this right. Okay. How do we skip? Oh, okay. Wait, what? How many questions?
59.
Okay. All right. I'm still so bad at the molarity ones.
Mm. So what is molarity like if you like broke it up into units?
Grams per mole or moles per liter.
Mm-hmm.
If it's in volume, then we want liters, right? So
Mm-hmm.
Ca and I, we have to figure out the molar mass of both of those.
Why?
Isn't that how you do it? You do 40.1 times 280 because it's Ca. I know it's I2. So 40 plus
I don't,
one.
why are we doing that?
I don't know. That's how I learned how to do it. And then you set up the proportion, and then it's like if you want to go moles to grams or grams to moles.
Yeah, but why would we do that here?
I don't know. Never mind.
Mhm. So what is molarity stand like? What is it in units if you break it up?
Moles per liter.
Okay. And what are they giving us?
Mole.
Okay. And what are we
Set
trying?
up with proportion like 0.120 is equal to 0.078 over liters.
Yeah, you could do it that way. But mostly you could just see that 0.12 moles over liters, and you can like divide that by 0.078 moles to get your answer in liters. Or I guess
Okay.
0.078 moles divided by 0.120 moles over liters, and the moles will just cancel, and you'll get your answer in liters. All right.
So then it's 0.78 divided by 120.
0.120.
Yeah. Since it's about half, is it going to be 2? Like double?
Um, you could try doing the math.
So 0.08 times 0.1,
Why are you
right?
applying them?
Because isn't it? Oh, it's 1 over 120. Wait, cancel. 8 is, I don't know how this helps, but 4/6. It's the long one, right? That is like 6, 6, 7, which is kind of like B, right?
Like, do the actual math.
I did do the math.
I mean, do it in full because you're getting the wrong answer.
Like with these numbers.
I
Or
mean, just the math, do the math fully. Like, what does this end up as?
what is which?
Your answer.
0.6 liters.
Mm-hmm.
So times 4, like times 1,000 gives D 600.
Yeah, so you definitely want to make sure you do this fully, like
Mhm.
meaning, you have moles here, liters here. Your moles cancel, you get liters. You want to make sure because they're not gonna be nice like this where, you know, like because you have the 65 and the 650. So you want to choose B without even looking at D. So you definitely want to make sure you do the math fully and
Okay.
account for the units.
All right.
Mhm.
All right.
You should plug your thing in.
What time? Fine. I'm confused. Why did I go back? Did I not? I don't understand.
You could just hit done reviewing and then just go to the BB directly.
Okay. And then I got 4 wrong too. So should go over this passage.
Mhm.
All right. Let me move so I can plug in my computer. Okay. About 15% of colorectal cancers or colon cancers are caused by defects in the mismatch repair system that corrects certain DNA replication errors. In some cases, this MMR defect contributes to the microsatellite instability, MSI, which is characterized by genetic hypermutability in DNA microsatellites, small repeated sequences that occur throughout the genome. Researchers studying MSI in CRC cell lines and primary tumors observed that 100% of those analyzed contained deletions of 3 to 8 base pairs in the 17 thymine nucleotide microsatellite T17, located in the intron 8 of the gene encoding heat shock protein 110 HSP 110. HSP 110 can bind structurally similar heat shock proteins and functions to facilitate proper protein folding and to reduce levels of non-functional protein aggregates. The larger HSP 110 T17 deletions cause exon 9 to be omitted from the final sequence during pre-mRNA processing. This generates a premature stop codon in exon 10, resulting in the mutant protein HSP11O delta E9. People with MSI-CRC have those transcripts in cancerous tissue only. Table 1 shows, with respect to T17 deletion site, the amount of HSP11 mRNA expressed relative to the total amount of HSP11 mRNA expressed in the MSI-CRC primary tumor cells. The total amount of HSP 110 mRNA expressed includes both wild-type HSP 110 and the mutant one mRNA. And then 2 tables, 3 tables.
So what do you see in these tables and stuff?
The size
Mm-hmm.
of the deletion
Mm-hmm.
and total and the percentage of this mutant
Mm-hmm.
HSP that it gets expressed. So the larger it is, the more that gets expressed.
Good.
Looks like it goes up linearly.
Mm-hmm.
Okay. And this table, what does endogenous mean?
Endogenous, it's from within the body, as opposed
Oh,
to endogenous, which is taking something that's from the outside of the body, putting it in.
uh-huh. Okay. So when none of the normal HSP is expressed, then 100% of the shock protein aggregation.
Mm-hmm.
Okay, and then when it's wild type. So what's the difference? Oh, because this is still something different. It would just be this if it was. So they're studying wild type and mutant on their own and then combined the percentages of all this stuff.
Mm-hmm.
Locations, and then there's a graph that correlates with this. Well, actually, tumor volume and time after injection. And so the wild type volume is greater.
Mm-hmm.
Okay. Based on the passage MSI-CRC primary tumor cells, the size of the deletion is inversely correlated with percentage expressed. It's directly correlated. So the bigger it is, this less normal HSP is expressed.
Mm-hmm.
So this it's directly correlated with
Mhm.
number of wild type, wait. But it's not wild type that we're looking for, right? The total amount expressed includes both the wild type and this one. So if there's more of this, then there's less of this one. So it's B. Cool. Okay. But wouldn't it be looking for the ones that are correctly bound to each other? So G goes to C, so that means 1 and 2 are wrong. Mismatch repair system. So in the opposite direction, 3 it wouldn't detect, but 1 and 2 would detect. Okay. I don't know what a clathrin is.
It's like clathrin coated pits, I think I remember. It's like something that can help vesicles.
Okay, so not this.
Mm-hmm.
I think it's a chaperone because it's not a, or no, a chaperone.
Mm-hmm.
Right.
It like
Okay.
helps the thing, the whatever protein folding or whatever it's trying to do, helps it along, like a chaperone.
Okay, and then an adhesion would be like the mutant protein, or no?
I forgot what the mute if it makes aggregates. I mean, well, adhesion means like sticking to something, right?
Mm-hmm.
So if it was something that helped things stick together, like cells sticking together, that would be something that adhesion would probably do.
Okay, all right.
Apparently, and the closest thing I could see to that is aggregates. I don't know if that's what it means by adhesion, but my guess is that, well, it reduces that, so yeah, it probably isn't going to be causing any adhesion,
Okay.
but it just helps the protein folding, so should be chaperone.
No, I get it. I just
Mhm.
should I check how many of these?
What's up?
I got, although like it's an amino acid one, so
What about?
I'd wanna do I feel like I want to do as many amino acid ones as I can
Mhm.
with you.
Yep.
Okay. Malnutrition is known to increase susceptibility. Okay, never mind. I started thinking of tryptophan and then STY and I got distracted.
Mhm.
Um, is known to increase susceptibility to colitis. Colitis can also be caused by pellagra, a condition that may result from tryptophan deficiency, and heart nut disease, a condition resulting from decreased functioning of the small intestinal neutral amino acid transporter AT1.
What
I
can you
think I literally just read A.
what can you tell me about tryptophan?
Tryptophan is part of STY, so it's charged.
Nope.
Polar.
Nope.
It's not part of STY.
Correct.
Tyrosine, not tryptophan. Tryptophan is non-polar. Sweet
Mhm.
treats and always taste good. Okay.
What was that other thing?
Sorry, I'm just thinking of the mnemonics.
What did that mnemonic say about it?
It's non-polar.
Anything else though? Well, I guess you can well, all right. You can continue.
Um, Continue reading or
Uh yeah. I mean, wait, did you get more than this one right for this? I mean, more than this one wrong for this passage?
9.
Okay. Yeah. So tryptophan is going to be one of the ring uh
Yes, it has the
acids.
I'll hit this. It has NH and then the like ring.
So this one they're a little like nice with because like we know lysine and glutamate are charged, so those are out. And they mentioned like neutral, right?
Right.
Also, oh yeah, arginine as well is out because these are positive, this is negative. But they could have made this more difficult by putting like maybe like let's say serine here, right? And then you would have to make a choice between serine and phenylalanine because they're both going to be neutral.
Should
But
we look for another one that has the ring structure and that's why
yeah,
it's spelling?
yeah. So it's just that the choices here make it so that even if we didn't know that there was a ring, we would be still choosing the only one that's, neutral, because they mentioned neutral amino acid. But they could have made it more difficult by putting in
But isn't
serine or
serine polar?
or something. What's up?
Isn't serine polar?
Yep.
So it's not neutral? Or it's like partially positive, partially negative?
Yep. So partial charges will still be
Neutral.
neutral, right? Um,
Right.
there's not a real charge, but yeah, I see what you're saying. Let's say that they put the valine, right? Then it could have been a little bit more difficult
It
to
was in that situation, how would I have figured it out? That
um
it was because the ring structure is like similar. Okay.
mhm.
All right. I want to go over this.
Mhm. Misosin.
Like it really sucks that they don't show me which ones I had flagged. I'm
Oh yeah,
sorry. I know
for
it's
that you
one
can
thing.
like I mean we don't have like if you want you can do it, but you could like we can like kind of look at the ones that you flagged and like write them down. Um like yeah.
I mean, like as we're going over it, I see that this is a concept that I don't know, so I'd want to go over it.
Mhm. Yeah.
Muscle contraction. I know myosin. I don't know what mysosin is.
No, I think that that's them making a mistake.
Oh.
Yeah.
Like I said calcium because I was thinking of like
Mhm.
muscles and
Yep.
like that's the one that I know is associated. Like people say calcium deficiency, you got like bone strength. I don't know. So yeah, like that's the one that I'd heard be spoken about with these things.
Yeah. So yes, okay. So the myosin, right, makes has like the head that can attach. Let's say this is myosin, also known as the thick filament, and then actin, the thin filament.
Like
And
muscle,
it's gonna
right?
be like this because they're gonna be attached, anchored at different points. Um, but what happens is the myosin head can bind to the actin and undergo like a conformational shift that will move it from like a 90-degree position to a 45-degree position. So when it's attached like this and it goes to 45 degrees, it pushes the actin this way and the myosin goes that way. And that's how you get your muscle contraction. Now, the calcium, what that does is, so typically the actin, the sites on the actin that the myosin head can bind to are covered up by something called tropomyosin. Just think of it as like kind of like a I don't know, like a string or
Wait,
something. Like yeah, covering like the
myos.
yeah the I think troponin or something it's called. But basically, the calcium is going to what's that? Oh yeah, that's what. Okay, yeah. So the calcium binds to the troponin and it causes the tropomyosin to move, to kind of shift, and to make those the sites on actin where the myosin can bind to, it exposes those sites, letting the myosin head bind to the actin, starting off
Okay.
that that cross bridge.
For calcium to cross. Because NAK is a like membrane, so that's not a cross bridge.
Yeah, this is happening in the neuromuscular junction. And something they also could ask you is where the calcium is being like sequestered. So I'm putting an image in the oh, hold on. It's a transparent image, so I have to screenshot it 1 second.
Do you see the one that they gave?
Yeah, okay, so here, 1 second. Okay, open this second one that I put in there. So here we go. Yeah, so we have the neuromuscular junction here, which is the interface between the neuron and the muscle. And we have this so the endoplasmic reticulum of a muscle cell is called sarcoplasmic reticulum. And that's this thing here that sequesters all of the calcium ions. And the calcium ions, like prior to all of this, if the neuron releases acetylcholine, which is the neurotransmitter responsible for muscle contraction, it releases it and into these acetylcholine receptors, which are basically ligand gated sodium channels, because once the ligand, which is acetylcholine, binds to the receptor, it will open up the sodium channels, allowing the sodium influx and that action potential. And what that also does is in the sarcoplasmic reticulum, it takes these calcium ions and releases them like this. And well, I guess this doesn't have as good of a picture as this one does, but here you can see that there's this tropomyosin blocking the sites that the myosin head can bind to. And when calcium binds to that, it shifts it so that those sites are are exposed for the myosin head to bind to.
Okay.
Yeah. Here you can see, I guess, step by step. acetylcholine released, action potential, calcium is released, calcium binds troponin, cross bridges form between actin and myosin. Acetylcholinesterase removes like leftover acetylcholine here. Oh, you can see it like this on the right side. So acetylcholine just gets kind of brought back into the whatever, the neuron when you use the amount that you need.
Okay. All right. I think this was a guess.
Mm-hmm. Yeah, so steroids are called that because they are derived from cholesterol. And cholesterol is derived from squalene, which is derived from terpenes, isoprene units. But basically, they look like this. Oops. Yeah.
That's the four.
Yep. And since they're
Because I
non
remember, because I remember when we do squalene, like they were open. I actually do. Yeah, we did speak about this. I remember.
Yep. And so yeah, so these are non-polar. Like things with rings are generally going to be non-polar. I mean, of course, there's going to be polar stuff attached to it, but overall it's non-polar, therefore hydrophobic. So steroids, like they don't need to like attach to a receptor on our cell. They can just go right through the cell membrane since the transmembrane domain is hydrophobic, right? So it can just travel right through, and it can travel right through the nuclear membrane too and go right into the nucleus and cause transcription of stuff. That's what they can do. And yeah, they're composed of rings, and they come from cholesterol, which comes from the squalene, which comes from a bunch of the isoprene units, which are the 5 carbon units of terpenes. So I think it's something like this or something like that. But yep, 4 weeks.
Concentrated urine is produced. Okay, I remember, like in my head, I was thinking that it would collect, and then
Mm-hmm.
I'm not sure what a convoluted tubule is.
So your nephron will look like this. So you have your like a bunch of capillaries here, which is your glomerulus. You
Okay.
have the beginning of the nephron tubule here called the Bowman's capsule. This is, you can think of it as like, since it's a bunch of like these bunched up tubes, that it's convoluted. Maybe that helps. I don't know, but that's kind of how I think about it. It's convoluted. It's a bunch of stuff that's bunched up, and it's in the front. So this is the proximal convoluted tubule. You have
Okay.
your loop of Henle. You have your descending,
This stuff.
your ascending loop, and around here is what separates the cortex from the medulla. And as you go down deeper into the medulla, the concentration of solute increases. So that's why like one of the things you'll see for the descending loop is water leaving, which means that it gets reabsorbed. It doesn't mean that like the thing is that there's also a huge like capillary network around all of this called the vasa recta. So that means that if things are leaving the tubules, they're entering back into the blood, and we call that reabsorption. Whereas if it's entering from the blood into the tubules, it's filtration. And the filtrate ultimately gets excreted as urine, but
Mhm.
the stuff that comes out, like this H2O, gets reabsorbed into the bloodstream. And That's going to happen because, yeah, we have a higher solute concentration down there. But yeah, then you have your ascending limb, you have your distal convoluted tubule, and then lastly, your collecting duct, which is the last part of the nephron's tubule, which eventually connects to like your ureter, which goes into the bladder, which then connects to the urethra, and then out comes out the urine. So that's the nephron. And now they're saying when concentrated urine is being produced, which of the following regions of the kidney will the glomerular filtrate reach its highest concentration? So, what are your
So
thoughts?
that we said that the glomerular thing was here. So I'm assuming it'd be close by, right? And since we said that this whole area is convoluted and it's in the front next to the glomerular, isn't it PCT?
So, if the solute concentration goes up as we go like down, that means that
Concentrated urine, which means that there would be where the highest concentration is. That would be towards the beginning of it, right? Because it's like flowing out from the kidney into the urine, into the from the liver to the kidney.
so for instance, compare the PCT to when you do this descending loop, right? The descending loop, since we're entering a region of higher solute concentration, it should suck the water out from the tubule, right? Thus making the urine inside more or less concentrated.
More because it would go out into it, no?
Uh-huh. So as we go deeper into the medulla, the environment, the outside environment has more solute concentration, which means that water will be sucked out as you go deeper.
Deeper. So that means that, oh, that makes it concentrated. So that would mean in the collecting duct,
Yeah.
except it's not cortical, it's medullary. So it's D.
Mm-hmm. Yeah. And also, you could see that, yeah. Well, yeah, there's that, but in the choices, if you could show those. So this is entirely in the cortex.
Right.
This entirely in the cortex. This, of course, cortex, and this is medulla. So that can also.
C isn't possible.
Well, the collecting duct does
Because
have.
isn't this the distal convoluted tube, and that's the last step of the cortex, and then it goes into the medulla.
Yeah, sorry, that's just maybe an issue of the way that I drew it, but it should be like, let's say, like that. So part of the collecting duct does also.
Okay, all right. Like I thought NAK plus is ATP, so I thought that ADP wouldn't be a part of it, but ATP to ADP. Okay, never mind. That's stupid.
Does not measure the activity of the sodium-potassium ATPase. Since it's an ATPase, it uses the ATP to make to do its job, right? And that could involve ATP hydrolysis, which breaks a phosphate off of ATP, creating ADP. So C could also be something that it does, right?
Yes.
So Now we have to think, okay, so if it does those, it can't be those, right? Because it says not.
Mhm.
Okay. Now what can we do here?
Membrane protein that maintains concentrations within the cell. So D is possible too. Right? Because liposome.
Uh-huh. Yeah.
So it's B.
Yep. Because yeah, if we check the ion constant, I was like a little weird about the liposome part, but yeah, if we see like, okay, we're having an increase in sodium and whatever, decrease in potassium, like, or the other way around, that means that this ATPase is working. So,
It's
uh,
hard to measure.
uh-huh.
Like, how does B work?
Measuring the free energy of ion transport.
Not like Gibbs.
Mm-hmm. Yeah. So
That's
maybe,
nothing to do with ATP.
yeah, I think, yeah, I guess that doesn't really measure the activity of the ATPase if it's just measuring the like Gibbs or whatever of the ion transport.
Okay.
Mhm.
Should we read this?
Um, we may not need to, or we may just need to read the first.
Let me check if I got. Okay, so I got 19 wrong. Right. So we only have to do 18. Like the first till here. Right here.
Probably just the first paragraph.
Okay, the cellular membrane potential is primarily determined by the concentrations of Na and K. The NAK ATPase is a membrane protein that maintains the concentration of these ions within the cell. In addition, the concentration gradient established by the NAK ATPase is used as the driving force in the co-transport of other biological molecules. Recent studies have shown that there is a correlation between decreased heart function and decreased NAK ATPase.
All right.
I feel like that didn't give me anything for this question. Action potential.
Yeah. Okay. So let's think about it then. Well,
Well, they're saying that decreased heart function and decreased NAK is so then action potential would be
so let's think about, okay, so what does this ATPase like actually do? Like,
it,
mhm.
ACE makes it okay, no, it's a protein. Um, concentrations of sodium and potassium within the cell.
What does it do exactly?
It maintains the concentrations within the cell of those ions within the cell.
When you say maintains,
It keeps them in equilibrium.
mm,
Not equilibrium, but like facilitates the transport. So it's essentially like a membrane.
so what's the
Across the membrane, the like NAK channel. It maintains the NAK channel into the cell and out of the cell.
what's the resting membrane potential for like a neuron?
I don't know.
Um, like, would it be a number like negative number, positive number, 0?
Membrane potential always like it can never be negative.
Uh, so okay, let's think about maybe what happens during an action potential.
I don't remember.
Um, maybe something like this. Like,
Like a graph,
uh-huh,
like those ones.
uh-huh.
It has to cross a certain. Is the action potential what it like has to cross in order for the reaction to take place?
What do you mean when you say cross?
Like, where's my thing to draw? Like if it's like,
Okay.
isn't there something like this that it has to get above in order for the reaction to take place?
So
Here.
the um
This is the action potential, I think, and this is like resting. This line.
so the neuron compared to the so like in order for this to go up here, what must be happening in terms of like the neuron's potential?
Say it again.
So for this to happen, what happens to that potential, membrane potential?
Increases.
So increases like tell me a little bit more.
Like, okay, so there's like a threshold that it has to reach in order for the reaction to take place.
Okay. But I'm saying this part.
Right, that it's going up.
So that means what?
Action potential.
Yeah. But I mean what's happening in terms of like
Like,
the cell potential, like of the neuron.
I don't know.
So it gets more positive.
Yeah,
So how does it do that?
like a substrate binds to it.
So okay, so I guess let's go.
And
So basically you're gonna start off at -40.
neurons fire because of a signal, so it's stimulated by something, right?
So first of all, we start off at -40.
Yes, and it goes up to 70.
Oh,
Positive.
sorry, -70. So that's our resting potential. Okay.
Yeah.
And yeah, we have an action potential happening. What happens is so there's relatively low sodium concentration inside of the neuron, and relative to the outside, high potassium concentration. So outside, high sodium concentration, low potassium concentration, right? So the resting membrane potential is -70 millivolts. Important thing is just to recognize that it's negative. Um, and let's say a threshold is reached, and then we have our action potential happen. So though the first thing that happens is it goes up like this, right? Now, if it goes up like this, it means
And
that,
it's come back down, right?
well, let's focus on going up though. If it goes up, what happens to it, to its membrane potential?
It increases
So tell me what that means in terms of ions.
positively charged ion.
Yep. So we should have so would that so that means that the neuron's potential is going to be more positive, right?
Mm-hmm.
So what happens is, well, if you have an option of opening a sodium channel, opening a potassium channel, which one would give you this increase?
High Na plus.
So what are you saying exactly?
I don't know.
So if you opened so let's just say that this is a channel for sodium and this is a channel for potassium, right?
Right.
Which one would you open to make? So if you open the potassium one, what would happen? Like what would the movement be of the ions?
Out of the cell.
So if it's moving out, we're losing positive charge. So that's not what we're seeing here, right? Because we're seeing the membrane potential get more positive.
That means it's Na.
Yep. So the sodium channel opens and then the sodium goes from high to low, right? So we get a sodium influx, right?
Mm-hmm.
And that's why the membrane potential starts to go up and it'll go up to like around 40 positive millivolts. And then
Mm-hmm.
the sodium channel closes. But what channel do you think will open?
Potassium channel.
Yep. When a potassium channel opens, what happens?
It goes down, negative ions.
And what happens to the potassium ions?
They go into the cell.
So if that happens, why would they become more negative?
Oh, sorry, out of the cell.
Yep. Because you have a higher concentration of potassium inside compared to the outside, right? So when this opens, you get potassium efflux. So sodium influx for this first phase, which is called depolarization, right? And then for the second phase, it's repolarization. Because if you think about it, if we're starting off at -70, we start off with some non-equilibrium value. So that's why they can call that polarized, and they can cause the opposite to be depolarized, or call it that. And then the opposite of depolarized would be repolarized. So that's when you have your potassium efflux. Now, the thing is, when you have your potassium channel open, it's slow. I don't know why, but it's just slow compared to the sodium one. So it's slow to close. So it's going to overshoot that repolarization step to be to give you a membrane potential that's more negative than the resting membrane of -70. And that's called hyperpolarization. But then it'll go back to normal and it'll be normal. So that's the entire action potential. Now this question is asking us, because in actuality, right, why wouldn't, there be enough sodium leaving, or sorry, enough sodium entering and enough potassium leaving to be at equilibrium, right? Because that's what it should be. It should have a net charge of 0, right?
Mm-hmm.
Right? But it doesn't, right? It has a net charge of -70, right? That means that something is using energy to create that concentration gradient. Gradient means difference. So something is using energy to create that differential, that charge differential.
Mm-hmm.
Because if we left it up to equilibrium, you should just get a 0 charge here. So something is happening that's using up energy to create a negative charge in the inside of the neuron. And what that is this right here. This pumps out to sodium. I think I might be mixing this up, but it's like, yeah, it'll pump in 3 potassium to give you a net negative charge. Wait. Out 2 in 1. I think I'm doing this the other way around. Um, this is, oh, okay. So it's 3 sodiums pumped out for every 2 potassiums pumped in,
Mm-hmm.
which is going to mean, so 3 plus out, 2
2
plus,
plus in.
so we get a net negative charge inside of the neuron. That's why that resting membrane potential is negative rather than what it should be at equilibrium, which is 0. So the sodium-potassium ATPase, that's also why it's an ATPase, because it takes energy, because energetically favorable would be equilibrium. So since it's not doing this, it's not maintaining an equilibrium, it's making it not an equilibrium. It needs energy in the form of ATP to create that non-zero, non-equilibrium membrane potential.
Okay.
So for each of these, stimulation of the action potential, that's if you have something like, let's say the threshold is like 60, negative 60 millivolts for like an action potential to actually happen and cause the depolarization. Like that could be like the thing that makes the membrane potential go a little bit more positive so it can start the action potential. Depolarization is when you have the sodium channels open and the sodium ions influx come inside, which makes the overall cell potential more positive. Hyperpolarization is this phase when it's getting to be like it overshoots it and makes it more negative momentarily. And these are all done by different things like stimulation of the action potential just from a change in voltage. Depolarization is when a sodium influx happens and the sodium channel opens. Hyperpolarization is when potassium efflux happens and therefore potassium channels are open. But the ATPase is just the thing that maintains this negative resting potential. So that's its function, to restore. So if they're asking what's the function during an action potential, it's to restore that resting potential of negative 70.
Okay, so then as far as this one goes, depolarization would decrease it, right?
You're saying,
Like we're saying that we want to restore the negative 70 on the graph.
oh yeah,
Wouldn't that be depolarizing it because that would give it a negative charge?
it starts at the negative 70.
Right.
And then depolarization means sodium influx. So it
Would
becomes,
it be like literally just restoring the negative 70?
uh-huh,
Okay.
yeah. If you hit the solution, they have a nice graph, like a thing here. Yeah.
Oh, I'm still on annotate.
Yes, here we go. So this has everything. So you see it starts at negative 70 and some stimulus causes a change in this voltage. And if it reaches some threshold value, like if so here it's not reaching the threshold, so it's going back to negative 70. But here it reaches the threshold. And if it reaches the threshold, that action potential starts and you have depolarization. So you see it going from this negative value all the way up past 0 to some positive value. And that's when the voltage gated sodium channels open and sodium influx happens, which makes the resting potential more positive, right?
Mm-hmm.
And up until this top part, that's when the voltage gated sodium channels close and the potassium channels start to open, which now means potassium efflux. We're getting rid of positively charged potassium. And that's why the membrane potential becomes more negative. And that's the repolarization. Okay. And here we could see that the K plus, oh, sorry. Here we could see that the K plus, like, I guess they're calling it leak channels, but the actual channel that was opened up for repolarization still open because it's just slow to close. So we have a hyperpolarization here, but it does go eventually back to the resting membrane potential. And so the
Okay.
entire question is asking us, what's the point of the sodium-potassium ATPase? And the point of it is it maintains this -70 resting potential, which
Mhm.
takes energy to maintain because it wants to be at equilibrium.
Okay. Got it.
Mhm.
Okay. All right. Should we stop here?
Yes. So tomorrow you're taking your next test.
Yes. And then as far as the schedule goes, like, so Monday I scheduled you, so then it's just Tuesday and Wednesday if you can find a time to meet with
Yeah.
me.
So I'm trying to move someone because on Monday, can you do like a longer session?
Yeah, yeah, I can do,
So
yeah.
I'm trying, yeah. So I have someone at 3 that I'm trying to move to either Tuesday or tomorrow. And if I can move them, then we can, when we meet on Monday, we can meet for like a really long time. And for Tuesday, I'm gonna message someone that I have at 6 to
Okay.
see if I can move that person earlier. And
Okay.
then I would try to put you in for 6 if that
Of
works on Tuesday.
course, whenever.
And then
Thursday, you said 6.
yeah, Thursday 6.
Okay, so I should be done with my preview. I don't know how long it's gonna take. It started 3:15
For the Thursday you're saying?
or 2:15, right?
Uh-huh. Yeah.
No, 3:15, yeah, on Thursday.
Uh-huh. And so, and then for Wednesday, I will see if I can move some people around as well. Okay.
Okay, thank you so much.
All right. Good luck on your test tomorrow. All right.
Okay, thank you so
Take care.
much.